Good morning everyone. Today I, Shourya Vashishta and my group from the M4 batch shall be presenting our project video on propeller and Kaplan turbines. In our group we have Shashank Sharma, Shivam Agrawal, Shivam Pal, Shourya Vashishta, that's me, and Shrish Bhalotia. The particular order in which we would be covering up the sections of our video are as follows. Now to start the video with introduction on propeller turbines, we have Shashank Sharma.
Everyone, next slide please. A propeller turbine, which comes under the category of axial flow turbine, is a reaction turbine that might be considered as a logical evolution of a Francis turbine to meet the particular needs of higher speed specific speeds. The limiting case of high speed Francis turbine, with the shroud removed and number of blades reduced, it is a propeller shaped runner. The specific speed is higher, and this meets the need of a turbine for relatively large flows under small heads. The resulting runner shapes in the propeller. Being a reaction turbine, the components are essentially the same as that of the Francis turbine. Next slide please. The components include scroll case, guide vanes, propeller shaped runner, governor, world chamber, and draft tube. The basic feature of a propeller turbine is that the flow is axial, hence its generic name is axial flow turbine. The number of blades is small and is in the range of 3 to 8. An axial flow turbine is capable of handling large flow rates than a Francis turbine because the meridional velocities are higher. Another way of looking at it is that for a given discharge and head, propeller turbines have smaller size compared to an equivalent Francis turbine. Next slide please. A Kaplan turbine is a propeller turbine with additional features of mechanisms to regulate the pitch, orientation of the blades to the direction of flow. This offers the flexibility of changing the blade angles at off design points to achieve maximum efficiency. Next slide please. The main components of Kaplan turbine are as follows: scroll casing and stay vanes, guide vanes, whirl chamber, propeller shaped runner, draft tube, and governor mechanism. Next slide. In scroll casing, it is a spiral type of casing that has decreasing cross-section area. The water from the penstock enters the scroll casing and then moves to the guide vanes, where the water turns through 90° and flows axially through the runner. It protects the runner blades, guide vanes, and other internal parts of the turbine from an external damage. Guide vanes. Guide vane mechanism, it is the only controlling part of the whole turbine, which opens and closes depending upon the demand of power requirement. In the case of more power output requirement, it opens wider to allow more water to hit the blades of the rotor, and when low power output requires, it closes itself to seize the flow of water. The space between the guide vanes outlet and the inlet of the runner is known as the whirl chamber. In this chamber, the flow changes from radial orientation to axial direction. The lower portion of this chamber, that is the immediate vicinity of the blade, is known as the runner chamber. Next slide please. The runner is in a Kaplan turbine, and in the propeller turbine is a set of specifically designed blades that gives the appearance of a ship's propeller. There is no shroud covering the tips of the blade. The blades are connected to the drive shaft at the hub. Now moving on to draft tube. A draft tube is an essential integral part of a reaction turbine and plays a significant part in the installation of the turbine unit relative to the tailwater level. The hydraulic aspects relating to draft tube installation are the same as described in connection with Francis turbine. Next slide. Now Shivam will take over.
Hello everyone, I am Shivam and I am going to explain the topic analysis procedure for axial flow turbines. So here, as my partner till now explained about the turbines and other things. So first of all, we should note the axial flow turbines. So axial flow turbines are the turbines in which the fluid flow is in the direction of the axis of the shaft, or we can say boss. And from here we can explain further about analysis. So figure is a definition sketch of Kaplan turbine. Figure shows inlet, which is guide vanes, and the outlet is the lower area, and it consists a turbine which consists of runner and hub and blades. So we have to describe some variables in this so that we can analyze our uh, thing. So outer diameter of the runner, d d is most commonly used as the Kaplan turbine diameter. So th is the diameter of hub, dm is the diameter of runner corresponding to the mid radius. Use peripheral velocity at any radial distance, and v is the absolute velocity at any radial section, and v is the relative velocity. So here we can see the two the two velocity triangles, and the one we have described as a inlet triangle and two is described as the outlet triangle. So here we can see the u1 is the peripheral velocity, and which is equals to u ultimately, and u2 is also equals to u, and the inlet angle is u is between u and v1, which is called alpha 1, and the and other angle is beta 2 beta 1. So this charge is axial to the plates because it's axial flow turbine. So as such, the area of load is this, and k is the net area factor after deducting for the area occupied by the plate in the cross section. So a is this and discharge is this, which is a multiplied by vfi. Vf is velocity flow in which constant entire the inlet outlet space. Let u1 is equal to peripheral velocity at inlet at any radius, and u2 is the peripheral velocity at outlet. So u2 and u1 is equally, when we already discussed about these things. And alpha 2 is 90 degree because it's coming from horizontally and going vertically. So alpha 2 is ultimately 90 degree. So the flow entering the whirl chamber from the guide vanes creates a vertex and runner. So we RH is equals to dh, from we can make an understanding from this, and RT is equals to di upon by 2, and so these terms remains constant, and v1 x is the velocity whirl at given radius x and left side of the blade. The Euler's equation is applicable with like this. We have discussed Euler equation previous chapters, and so ultimately we can derive hydraulic efficiencies this, and h is net head. So beta 1 and beta 2 is outlet change all along the blade line. The velocity triangle at inlet and radius is on the blade in actual angle triangle. So this is some graph between the radius ratio and the angle alpha and betas, inlet angles and outlet angles. So what is an aerofoil? Aerofoil is a cross-sectional shape designed with a curve for lifting up for giving a lift to any object or flight and other things. So it is highly used in the aerospace engineering, and aerofoil depends on the aerodynamic characteristic, so which is further depends on the aircraft weight, speed and purpose. So airfoil are used in the design of aircraft propellers, rotor blades, wind turbines and other applications of aeronautical engineering. We have already discussed about that. So from here my partner will explain. Shivam will explain.
So hello everyone, I'll be covering the topic working proportions of Kaplan turbine. So in this topic, I'll be going into brief. Consider a Kaplan turbine with H, net head of the turbine, rotational speed in RPM denoted by N, power developed by it, and Ns is the specific speed of the turbine. So the number of guide vanes depends upon the diameter of the runner D1 and a range between 8 and 24. So the proportions to cover are relative guide vane passage size. It is a function of specific speed and its value is in the range of 0.30 to 0.41. Relative hub diameter, it varies with the specific speed and has a range of 0.40 to 0.64. And the flow ratio Kf, it is a function of specific speed and has a range of 0.35 to 0.75, corresponding to a specific speed range of 260 to 860. Coming on to the next slide is the flow ratio Ku. It is also a function of specific speed and has a range of 1.3 to 2.3, corresponding to a range of specific speed of 260 to 860. This is the table showing the specific speed and the speed ratio and the flow ratio in the below figure. And coming on to the next parameter is the size. The size of the runner of a Kaplan turbine is generally large and is the function of the head under which the turbine operates and its rated powers. This is the formula of the size. And coming on to the efficiency, the overall efficiency of the Kaplan turbine is very high, being about 93% for a well designed large unit. The runaway speed. Generally, the runaway speed of a propeller turbine is in the range of 2.5 to 3.0 times the design speed. The specific speed. The normal range of specific speed of Kaplan turbine is 260 to 900. Thank you. That's all from my end. I have covered all the aspects of the working proportions of the Kaplan turbine in brief, and we'll be hearing about them in detail by the other participants. Thank you.
This is Shivam Pal, roll number 2K20, ME 260, and the topic is variants of propeller turbine. First, I am discussing about what is propeller turbine. The propeller turbine is a type of inward flow reaction turbine with a propeller-shaped runner, which can be seen in ships and submarine, either fixed or adjustable blades. It is an inward flow reaction turbine similar to a Kaplan design, but with fixed blade. Types of propeller turbine: tubular turbine, bulb turbine, rim type turbine, and Darius turbine. So now the tubular turbine is such a successful alternative system of Kaplan turbine. The Kaplan turbine gives very low heads and high discharge, so we need to search alternative of this. Then we search tubular turbine of the search tubular turbine. In tubular turbine, it has efficiency that is about 1 to 2% than the vertical propeller turbine due to lesser hydraulic losses in the passway. Tubular turbine heads is 20 meter and the power range up to 7 megawatt. Main feature of the tubular turbine is a compact arrangement including turbine and generator with bearing with seals in a single unit. Construct with stainless steel, ability to install the unit vertically or horizontally. Heads ranging from 5 to 30 meter for most applications. Now the turbine is basically bulb turbine is an axial flow hydraulic turbine which consists of a bulb shaped body to accommodate generator run and draft tube and part of this generator. Now, the bulb turbine is proper for low heads less than 25 meter. The advantage of this turbine is that they take up little space due to the seal turbine and generator. The bulb turbine are also able to work in reverse flow direction. For very low head and additional speed of generator, bulb turbine are available to general power in the range of 10 to 100 megawatt. It is required appropriate cooling and air circulation inside the generator bulb. Next is rim type turbine. It is a compact propeller turbine with a generator built into the rim of the turbine runner. It is founded for small installation of 1 to megawatt and 10 to meter head. And now next The performance of the rim type turbine are similar to that of two bulb turbine. These turbines are available with or without wicket gates. Now the Dairy's turbine. This is invented by dairies in 90s. It is the most positive aspect of this turbine are that can have both adjustable and fixed blades. The hub contains servometer and operating mechanism, which helps in adjusting running blade according to load. It is suitable for power station where load variation are more. The advantage is that it has more efficiency at part load over the Kaplan turbine, having two specific and runway speed and higher cavitation coefficient than Kaplan turbine. It can also be used for reversible pump turbine service. Should be 90 meters. Thank you for the thank you.
Good morning, everyone. Now, I, Shourya Vashishta, roll number 261, shall describe the performance characteristics of the Kaplan turbine. These characteristics are studied under constant head, and variation is done for discharge, power, and efficiency of the turbine. In variation of discharge, unit discharge is measured against unit speed for 4 different gate openings. The curve obtained is an inclined straight line. In variation of power, the curve between unit power and unit speed is measured for 3 different gate openings, which is parabolic in nature. Lastly, in variation of efficiency, efficiency is measured against unit speed again for 3 different gate openings, and the resultant curve is parabolic. These curves are displayed on the screen as you can see them. Now onto cavitation on the next slide. Uh, Cavitation can be described as a process in which vapor bubbles are formed rapidly when the static pressure becomes smaller than the liquid's vapor pressure. These bubbles collapse when subjected to higher pressure and cause damage to the machinery via the kinetic energy that they release. In Kaplan turbine, this phenomena occurs extensively due to its high specific speed and low head usage. Some areas of turbine are more susceptible to cavitation than other, like the draft tube liner, hub, trailing and leading edge of the blade on pressure side, discharge ring, etc. All the others can be seen in the diagram given on the screen. There are also the most probable causes, and the remedies have been mentioned for cavitation in the Kaplan turbine. They can be adhered to in order to reduce damage to the Kaplan turbine. On the next slide is draft tube. Draft tube is like a divergent tube fitted at the exit of the runner of the turbine to the tail race in order to utilize the kinetic energy available with the water at the exit of the runner to static pressure or pressure energy. There is a steady increase in its cross-sectional area from the exit of the runner to the tail race. This raises the water pressure to the atmospheric pressure. To tolerate the increased pressure and speed, the tube must be strong enough and is usually made up of cast steel and cemented concrete. There are certain things needed to be taken care of while designing and planning this tube, like frictional and form losses in the draft tube and susceptibility to cavitation. The high specific speed of the Kaplan turbine leads to high speed, low head, and high discharge installation. The kinetic energy leaving the runner is relatively very high, about 50% of the total input energy. This substantial energy needs to be recovered, thus the draft tube is used in Kaplan turbine. A schematic sketch and isometric view of an elbow type draft tube for Kaplan turbine has been shown on the screen. Also, one more interesting fact, that it is experimentally found that the efficiency and draft tube is The efficiency of the draft tube is basically increased drastically when the ratio of its height and inlet diameter is equal to 2.24 and the ratio of the length to diameter is about 6. Now passing on to Shirish.
Greetings, sir. Myself, Shrish Bhalotia, roll number ME262, and I'll be continuing and explaining about the general features of propeller, Kaplan turbine, and their variants. So, firstly, I'll be discussing about the key benefits of Kaplan turbine. So, this is basically a double regulation system which allows for high performance over a large range of head and discharge. And also, the Kaplan turbine are certainly the machines that allow the most number of possible configurations. Hence, the Kaplan and its variants cover the entire low head and high discharge range. And large Kaplan turbines are designed individually for each site at the highest possible efficiency at the available technology. And with the benefits, there also comes some concerns, which are such as low head axial flow turbines are susceptible to cavitation, and Kaplan turbines and bulk turbines are often installed on large rivers where fish ladders allow the fish to migrate upstream for spawning. And these large amount of fish have to go through the turbines. An efficient design to improve the survival of those species while they are migrating are needed and are being explored all over the world. So now we have a comparison of Kaplan and the Francis turbine. And to name a few, the Francis turbine has a scroll case and adjustable guide vanes, whereas Kaplan turbine has scroll case and adjustable guide vanes. And in the Francis turbine, the each blade, the inlet edge is exposed to the flow and only one inlet angle. Whereas for Kaplan turbine, the entire inlet edge from the hub of the tip is exposed to the flow and inlet blade angle varies from hub to the tip. And the Francis turbine has a draft tube. The Kaplan turbine also has a draft tube, but the design of the draft tube is critical from the consideration of cavitation. And Francis turbines are also susceptible to cavitation, but the susceptibility for cavitation is greater for Kaplan turbines. So in the end, so we have an illustration for the Kaplan turbine where we have to develop a Kaplan turbine which generates 7,350 kilowatts of power and the net available head is 5.5 meters. And the other information is given and we have to calculate the diameter of the runner and what is the outlet blade angle for the tip. So here's the solution for the same. We are given P is equal to 7,350 kilowatt, H is equal to 5.5 meters, KU is 2.2, KF is 0.68, mu naught is 0.90. And so for the tip of the blade is considered and suffix 1 refers to the inlet and the suffix 2 refers to the outlet. So V1 is equal to 0.68 under root 2 into 9.81 into 5.5, which is a constant. And then the tangential velocity is calculated at the tip. And then power is calculated in the formula naught gamma QH. And there Q is calculated by replacing the formula. And at the end, we get the value of Q as 151.67 and D is given as 5.5. And then with the outlet velocity triangle, we get the value of tan beta 2, which comes out to 0.309. And by inversing that, we get the angle of beta 2, which comes out to be 17.17 degrees. So with this, we conclude our understanding of Kaplan turbines and we end our presentation here. Thank you.